Welcome everyone to the class. See, general mathematical objective to solve the vanishing gradient problem. So, in a recurrent system, we have the hidden ht to be equal to some function f of ht minus 1 and xt. This is the definition of recurrence, isn't it? Current state is a function of the previous state and the current input. Look at our equations, no? ht is a function of ht minus 1 and xt. Of course, there is a sigma. I mean, all that is captured within this function f now. So there is linearity, then it's a composition. This capital F now is a composition of linearity and some non-linearity. It doesn't matter, but what is important is its function of ht minus 1 and xt, correct? So this implies that this particular Jacobian, which is a product of these terms, so dependence of the final hidden state on any previous hidden state is through this product. Oh, sorry. Yeah, this comes up because of the recurrent nature, correct? Now, in a vanilla RNN, vanishing gradients happens because since this term is multiplicative, we have diagonal of this sigma dash times w. Correct? Because of this repeated multiplications of w, we get that particular term. Okay. The solution is to make just approximately equal to identity. If you make this, then doesn't matter, right? I mean, this is the degenerative or naive solution, as he said, make lambda max equal to 1, so that there is a path from the outermost hidden state to the any hidden state without any linear multiplications of w, right? Now let's look at general principle to do that is to achieve this. Yeah, the state update should be additive in terms of instead of multiplicative. How do we do that? Make ht to be equal to some alpha t times ht minus 1. Actually, I'll write it as Hadamard product here, element wise multiplication, because alpha t and ht minus 1 are both vectors. I'll multiply each of the elements by something different value, beta t times h t tilde, where ht minus 1 is the previous state, ht tilde is some function of w1 xt plus some w2 ht minus 1 plus some bias. So alpha t and beta t are modulators, some okay, that's all. So now what am I doing is, look at this. Now the dependence of ht on ht minus 1, okay, is now additive, it's not multiplicative anymore. See, what was it? ht was dependent on ht minus 1 through sigma, through this equation previously. Now there is also an additive path here, you see this. So now ht depends on ht minus 1. Previously ht was dependent on ht minus 1 through this matrix and some nonlinearity. This f is some nonlinearity. Okay, I can write it as some sigma, some nonlinearity. Now to that we have also added another additive term here. Do you see this? Yeah. Now what happens because of this is that the derivative of hk plus 1 with respect to hk will now have two things. We will do that as well. One, there will be a term that still has this w term, which with the vanishing gradient thing, and there will be another term that only has this alpha t times identity, because this ht minus 1, the dependence is only linear here. You see this? That's it. So you are creating an unstopped or rather unrestricted conveyor belt kind of a thing from between states ht minus 1 and so on. We will do the math. I will show you the equations in a way. Yeah.
Is it possible that beta can modify itself in such a way that it cancels out?
Which one? The alpha meaning. Yeah, that can happen. Those are also learnable. I will complete the story in a while. Okay. Now what happens is, suppose you make beta t to be equal to 1. Okay, you get a particular type of an RNN called highway network. Okay. If you make your beta t to be 1 minus alpha t, then what you get is what is called as gated recurrent units, GRUs. Okay. If you make both alpha t and beta t to be learnable vectors, then it is an LSTM. In fact, this is not the only way to do this. That paper which I will share with you has shown thousands of ways to do this. Okay, that will ensure that all of them will have the same effect. But what is to be done is that the only thing is that you will have to ensure that there is a linear path, so that the derivatives will not die down. Let's look at the math now. No, we are not restricting the learning, because we still have this. No, we are not changing anything. This is like that skipped connection in ResNet. We still have that path. We have now two paths. There is a highway, or there is a linear connection, and there is a non-linear connection as well. So the gradients flow from both the ways. There is I mean, this alpha and beta will tell you how much of the information to forget and how much of the information to remember, if you look at it that way.
So out of the two paths, which path is the learning?
Depends on the problem. You leave it to the neural network. So you are learning alpha t and beta t as well, no? Right? So network will decide which one to what to remember, what to forget. But you are facilitating the neural network to forget, selectively forget and remember through this alphas and betas. That's it. See, I could have actually written the equations of GRUs and should all the complicated stuff. This is actually the most abstract way of looking at things. So you can derive thousands of architectures from this. Okay, let us look at the calculus right now. Let's look at what happens to the the derivative, so that this will not lead to the vanishing gradient problem. That's where we stop. Okay. Where? It doesn't matter. I think this is what did I write? Okay. It's just a parameter, right? Call it whatever. It has no bearing whatsoever. Just two set of parameters. It doesn't matter what it is. Okay. And by the way, some people call this this H tilde as candidate states. Okay. So there is some candidate state, and then you multiply that with lots of terms, right? Forget gate, input gate, that gate. Call them gates and so on. Basically, this is the idea. right? So yeah, okay. So let's look at the math. What happens at the math now? The gradients for the above networks. See, please don't complain. Don't tell me that GRUs and LSTMs was in the syllabus, but I did not teach them. I've actually taught the grandfather of GRUs and LSTMs, so you derive those things from these. Okay.
LSTM stands for.
Long short-term memory networks. There's a long-term memory, short-term memory. This HT tilde is the short-term memory, HT minus 1 is the long-term memory, and so on. It's Schmiduber's idea. So just go and look at LSTM equations and convince yourself that this is a special case of whatever I've written here. Okay. The power of abstraction, you see, always abstract, so that everything in the world becomes a special case. Okay. Okay, so let's consider this derivative, right? So H is consider this will now be the diagonal of uh, vector alpha t. So you understand what is diag means, right? It's a diagonal matrix with this alpha t as its diagonal. Okay, that's what I mean. And since we are looking at gradients, sorry, vectors, I'll have to write these this way. So ht minus 1 times diag of ht minus 1 plus dou beta t times h t tilde divided by dou ht minus 1. See, whatever I am doing it for this particular abstraction can be done for GRU separately, can be done for LSTM separately, and that's a homework. You understand what I'm saying? Write down the equations for GRUs and show that it does not have vanishing gradient problems. I'm doing it right now, but you'll have to do that special case. This is the most general case. Okay. Now this can be written as, so diag alpha t plus some epsilon t. So all these terms, simply calling them as epsilon t. Why am I doing that is because see here there is dependence on ht tilde and ht minus 1 and so on, which will have w1 and w2 terms. You see what I am saying? See, ht here depends on ht minus 1 and ht tilde. Ht tilde depends on xt and ht minus 1 through w1 and w2, correct? So these terms which I am saying as et or epsilon t, this actually depends on w1 and w2. I don't care about that. All I am looking at is diag of alpha t now, which is independent of w1 and w2. This independence is coming through this particular term. See, when I take the derivative of ht with respect to ht minus 1, there is diag of alpha t here, right, and the other terms. And these other terms I have simply used chain rule here, right? The first term plus the derivative of the second has product. So these two terms come from the product rule, that's it, correct? And I am combining all the terms that are coming from the product rule into something that I don't care. Okay, so now there is diag of alpha t term. Now when I take the derivative of the last state with respect to any time step t, which will now have the products of plus this term, right? Now if I do Cauchy-Schwarz and look at the norm of this, what will happen? There will be a norm of t to t to t minus 1, correct. T to t minus 1, some identity here, because the diag of alpha k plus 1, you take alpha k and it will become an identity which will be 1, that's it. So there will be that term. See now what happened, no, there is this additive term that comes up, okay. This first term, it can still have gradients, okay, without caring about the second term which has dependence on w. Do you see that, right? So because of the presence of this particular term here, it depends on what alpha is of course, but since we are making alpha to be a learnable parameter, if it needs to be identity, you can make it to be identity, right? Yeah, of course, well, that's the best that you can do. No, at least that's what I told you, right? We have facilitated the neural network to be able to learn the long term dependencies, that's it. That's all the point is. There is no, see, that's all every regularizer will do, no? Any regularizer is simply facilitating the neural network to operate in that high bias low variance region, that's it. Over parameterize and increase the bias. Now you see why this is regularizer, right? So I told you in when I looked at bias variance decomposition that every single architectural tweak that we do is a regularizer. Now going from RNN to GRU or an LSTM is an explicit regularizer where you have that additional path. It's like this. I'll take another question. It's like this, right? So you make y to be equal to x plus some function f of x. Y was f of x, right? Now you made it to be equal to x plus f of x, where x is the identity. This is the ResNet idea. This is the residual skip connection. See, this idea is so important because even the modern day transformer architectures has skip connections in it. All deep neural networks have a skip connection in it, in them, because you need to be able to learn this identity, that's it. The gradients will simply vanish. And please note that the identity that we are talking about in a recurrent architecture is through time, not through space. But in a ResNet, the identity is through space, not through time. So when you have neural networks that are, I'll just tell you what I mean. See, let's say that you have an MLP like this, right? This is x and this is y, you have connections this way. Suppose I take this and put it here and connect it to this layer without any weight. Sorry, this is plus. So this is skip connection. This is how it is typically done. Take one layer, the other layer of neural network, connect the output of that to the next layer. So that's skip connection, which is done in the residual neural networks or ResNet. Even in transformers, this is done. And now here doing it in spatially. What we mean to say is that in the it is done through, in the depth dimension. But in an RNN, we did it through the temporal dimension. Depends on where your vanishing gradient happens, right? See, you ask the question, how is an MLP related to an RNN? So I am giving you a hint. In an MLP, when you go from one layer to the other, the gradients flow from output to the input. If you look at each layer as a time step, then there is a vanishing gradient problem as you go deeper in the neural network, isn't it? That's exactly the problem the ResNet solves. If you make the neural networks, you know what the ResNet paper shows. It shows that deeper is not better. If you go deeper and deeper, the neural network starts performing worse because of this exact same problem, because the gradients have to flow. Now how do you solve that? Through the same idea, wherever you have this sort of a thing, ensure that the function also has an identity path so that the gradients do not go to 0, simple chain rule. So they did residual connections across space, meaning when you are doing neural networks, when you are constructing neural networks which are deeper, ensure that every layer has a residual connection so that there is a uninterrupted path so that the gradients can flow. Do the same thing across time in an LSTM. In fact, to make things complex, you can have an RNN, okay, which has longer context, and you have deeper RNNs as well. You realize what I am saying? And through the depth, you can have residual collections there as well. You see what I'm saying? There is an RNN, okay, where there is parameter sharing across time, and each RNN cell can be a deep neural network across space, and that deep neural network can have residual connections across space as well, have the same effect. I mean, gradients actually are flowing from two directions, right? And please note that across depth there is no parameter sharing. This is W1, this is some other W cap, there is another theta and so on. But across time the parameters are shared. That's now you can see why this is an MLP with a certain architecture, isn't it? Get it? So typically an RNN, the way it is implemented is that will be a part of your second assignment anyway. The way it will be done is you have a deeper RNN across space, and you already have parameter sharing across time by construction of an RNN. Okay. Any questions? You had a question?
So just the math in the last step and you're applying Cauchy-Schwarz, right?
See, yeah. So you'll have to have the other term also. There is a plus here, and you'll have the norms of these individual terms bounded, and I'll take this one term and then there is this DAG term which will have 1 as a gradient. That's what I meant. You have norm of sum of two vectors, then you have to bound that. Norm of sum of two vectors can be decomposed into individual norms, no? Yeah. So then you take one of the individual norms and then do it. That's it. Yeah. Okay. So this completes the discussion on the recurrent architectures, the LSTMs and GRUs, and thousands of them as well. Right. Please read that paper. I'll share that with you. Okay. Next class we will look at the attention mechanism and the transformers, which is the state of the art architecture. And then how are these neural networks trained? Still ERM with the same gradient descent that we are looking at, and you can still have all regularizers that are there. And remember that we are still trying to get that P of y given x by minimizing the KL divergence. So that does not change. Okay. Okay. Thank you then.